I hope you can hear me. Hello, everyone. Hello, everyone. Condition, you can hear me.
We can hear you.
Okay, great. Jenny, you can hear me. Hello, everyone. Welcome to Harvard CMSA Center for Mathematical Sciences and Applications Quantum Matter in Math and Physics seminar series. Today, we are very honored to have Janet Li Yanhong. Actually, it's Ling Xin Kong, and I'll explain her name a bit soon. And she's from Fudan University. It's a colleague of her and also a good friend of her. I'm very honored to say a few words about her. So her topic today will be gap boundaries junctions via fermionic anion condensations. And in the next three or 4 minutes, I will say a bit some background about Janet. And if you want to get tea and coffee, please. The topic may not be very conventional, so if you're not open-minded, then you may not want to hear. But in the next 3 or 4 minutes, you can just stay away. But come back. But if you want to hear a bit about Janet, then please stay here. So Janet's work is mainly on entanglement, topological phase of matter in aspects of condensed matter theory. But she also works on ADS CFT applications of string theory, quantum field theory, and black hole. As I mentioned, it's actually difficult to pronounce her name correctly. And I should mention first that her surname is actually Kong, the same as the Confucius, although it's spelled in the C-O-N. But the home of her name is actually a Cantonese way of writing. And some people may know the Confucius was born 550 BC, before this, the starting of the first century. And if you just try to write down the genealogy book from the Confucius, there are like several generations, and this will just be 1 page of 4 generations. And nowadays, right now, there's about 80 generations. And those 80 generations, you should imagine that if you write it down, there will be more than 20 pages of this. And actually, you will grow exponentially. And Condensation actually will be it's actually the 76th generation of the Confucius direct descendant. And her name should pronounce as, maybe Jenna, you can help me. Your Cantonese name?
Hong Ling Yang.
Yeah, Hong Ling Yang. And then the Chinese name will be Condensation. When I was at IAS at Princeton, Nati Cyber sometimes will be very enthusiastic, ask me about Chinese name. And sometimes I try to explain to him. But I noticed his enthusiasm fade away after 1 minute. I try to explain. And today I think I will try to begin a bit of work on how these names actually come about. And one thing one should think about is that there are already 80 generations since Confucius, and you can count. If I just the exponential growth, how are these people? Where were these people right now? 2 to the 80. Where are those peoples? These are the quiz for you. If you have an answer, you can post on the chat. Actually, I think it will be more challenging than you think. Yeah, this among people, you should think where they are. And actually, another interesting fact is that another colleagues, Kong Liang, many of you know, also working on the topic today about gap boundary, gap domain wall with Kitef. Actually, he is also a descendant of Confucius, and they share actually the same last name, if spelled in this way, Kong. However, as you see, the Cantonese spelling is different, so that's why you cannot distinguish this. You cannot actually tell they are actually all from the Confucius family. And nowadays, there are already 80 generations live in Taiwan. The 80th generation and 79, 80. They are probably the most latest generations. As some of you actually know that there are many tones in Cantonese. So the Cantonese tone, for example, would be 9 tones. And people like Janet, maybe Janet, you can pronounce this name for me. So Janet's name will be, please hail again.
Hong Ling Yang.
Yeah, Hong Ling Yang. But the Chinese name will be Hong Ling. And if you write it down the Cantonese name or the Mandarin name, you'll find out. Some people. Sorry. Yeah. So if you try to write down the maybe Jenny can help us. So Professor Yao's name will be Yao Xintong, while the Chinese name will be Zhu Centong. But the Jenny's name will be Hong Ling Yan, but the Chinese name will be Kong Ling Xin. So this actually point out a very interesting fact, and also other physicists you might know, like Kong Liang, it will be Hong Fan Long in Cantonese, while in Chinese it will be Kong Liang. And then if you try to write down the tone, actually a good way to write is actually in music tones. So it will be something like, the G will be so and C will be do. It will be so do do, so mi so, so do do, do so so. And if you pronounce all this name, you will find out that's a better way to pronounce all this name. So a question to you may be, why the familiar language perhaps we're using maybe an English name to name will be a good labeling for people, and sometimes it may not be. And for physics, it's also probably true that if we try to use the field theory or general relativity, maybe those labeling may not be called a good labeling. So I think today Jenny also address this type of issues. Lastly, I think I will skip this part. Let's just welcome Jenny now. Jenny, please take over. Gap boundaries and junctions via fermionic anion condensation. Please.
Okay. I'd like to thank Juven for his kind invitation and also his very extended introduction of his beautiful introduction of Cantonese. Today I'm going to talk about our very recent paper, gapped boundaries and junctions via fermionic anion condensation. This is some work done in collaboration with several very young people from Fudan University, particularly Jiaqi and Shen Se, and also Chao Yi. They are very brilliant young people who has taught me lots of things, and I'm very honored to have worked to work with them. Oh dear. Right. So, so the outline of my talk, I'll start with a basic introduction, to set this language, to set the notations. I'll give a very brief introduction of how to describe bosonic topological orders in 2+1 dimensions using unitary modular tensor category. Then I will review known things about classifying gapped boundaries and using anion condensation and Frobenius algebra. In particular, how boundary excitations work out and how excitations at junctions are worked out. Then I will move on to what we did. Basically, it's a modest extension of this previous work to include boundaries corresponding to fermions that condense at the boundary of anyons with fermionic statistics that disappear at a boundary that characterize that particular gapped boundary. As we're going to see, it would be this kind of fermionic condensates can be described by a so-called super commutative Frobenius algebra, which is a very direct generalization of the idea of Frobenius algebra. The main new ingredients that we will spend some time upon is that when there are fermions involved, there would be new types of objects in the condensed theory, namely these so-called Q-type objects that could hold Majorana mode, and also these odd fusion channels where they're also having some Majorana modes. So our main effort is would go into identifying these objects and these fusion channels and understand how to count the number of fusion channels and obtain fusion rules and so on. then I would put these abstract rules in very concrete examples, and finally I would summarize and give some outlook of this set of work. The reason why I put in this picture of the Russian dolls is that it appears that when we talk about anion condensation, it really has the flavor of understanding relationships between different topological orders, and the relationship, I feel like it's like a Russian doll inside another, and this there's a big web of relations. So topological order is a huge subject, and I'm just going. There's a huge number of references. I don't know where to start, and so what I am going to say is that there are a few hallmarks of topological order. I think the name topological order was proposed by Hexagon back in the 80s, and by now we understand that these are phases of matter that are not characterized only by symmetry breaking, and they have a long-range entanglement. And some hallmark of these phases is that there are anionic excitations which have highly non-trivial statistics. And when you put this in 2+1 dimensions, if I consider putting these phase on a non-trivial manifold with high genus, that would be non-trivial ground state degeneracy. And as I mentioned, these phases have long-range entanglement, and they would have non-trivial topological entanglement entropy, for example. So the properties that I just discussed, anyons, non-trivial statistics, this kind of properties can be very well accommodated, this data can be captured very concisely in the mathematics of modular tensor category. Actually, I also am not entirely sure where who are the first people who start to put the study of topological order in the framework of modular tensor category. I would be very happy if someone could educate me on that. But in any event, the topological phases of matter can be summarized very concretely, can be summarized very concisely in the mathematics of modular tensor category. And so what are the basic ingredients that are needed? What are the basic physics that goes into this definition of the modular tensor category? So the basic physics, sorry, yes?
It could be Moore and Seiberg. I'm not sure, but Sodi as Moore and Seiberg. You said that.
I see.
Yeah.
I'm aware of the work on rational CFT, but as far as so maybe that connection with topological order was based on the connection between transaminds and CFT. I don't know. Is that how things evolved? But thank you. So what are the basic?
May I ask, since there was a question about history, I think Moore and Seiberg studied only the rational conformal field theory, but they uncovered the full mathematical structure of the modular tensor category. This name and the mathematical framework for that was set later by other people. And I think that the connection to topological phases of matter was most clearly put forward by Kitaev. I think these are kind of the three steps. And along the way, there was Witten's work, which connected the discussion in two-dimensional rational conformal field theory to three-dimensional space. So my understanding of the historical order is that Moore, Seiberg, then there was Witten connection to three dimensions, then there was modular tensor category in the math community, and then Kitaev brought it to the Anion connection to topological phases of matter.
I see. Thank you very much. That's helpful because I was not entirely sure. I looked in Google a little, but I don't feel safe, and so I didn't put lots of reference there for fear of making things saying wrong things. Thank you. So what are the basic ingredients that go into this modular tensor category? So we have, as I just mentioned, in topological order, we know that there are anionic excitations, and these anionic excitations are simple objects in the modular tensor category. And by simple, we mean that these anyons do not have any internal structure. And so when you look into the mathematics literature, it is going to tell, it often talks about morphisms between these anyons. And so it is, if we look into the morphisms between simple objects, then it is always a one dimension. They only have a one-dimensional morphism space with themselves, and their morphism with any other simple objects would be there would be no such morphism between different simple objects. That would be the definition of being simple. And if I have some composite objects that is the direct sum of simple objects, then the morphism space would be multi-dimensional. So being a simple object specifically means that it doesn't have any internal structure, and the homomorphism would be trivial or only one-dimensional with itself. So this is going to be an important point when we generalize to fermionic systems. Because doing more non-trivial morphisms of simple objects within itself. Then we mentioned that anyons can fuse, and this fusion is also a kind of morphisms, and we can build basis for this fusion morphisms. And moreover, these anyons can run around each other. They could braid, and so there would be a braiding matrix that is defined. And there would be some consistency conditions that this data that goes into defining the modular tensor category. So for example, fusion should be associative, but it is not exactly associative, and it can be associative up to a linear up to a linear transformation. And suppose we are fusing these anyons at different order, grouping them in different orders, then there would be exactly one consistency condition, the famous Pentagon relation, that relates these 6J symbols or F symbols that connect different ways of grouping the fusion. So basically, so there would be an algebraic equation relating these F symbols. And another consistent relation is the Hexagon relation, which tells us that if we are braiding and fusing in different orders, there would also be an algebraic relation relating the R matrix and the F matrix. So this is something that you could look up in a book, and I will not say anything further. These are just the basic ingredients or basic consistency conditions that go into defining the modular tensor category. So let me just also say 2 words about the word modular. When we put the ground state, when we put the phase on a torus, we could do, there would be ground state degeneracy, and the basis of ground states can be constructed using anyons wrapping around a non-contractible cycle. And under modular transformations of these of the torus, the T transformation and the S transformations, these ground states would be rotated into each other. Corresponds to the eigenvalues of the T transformation would give us the spins, that are the self-statistics of the anion. And the S transformation, if we're working in the anion basis, it is going to tell us about the mutual statistic between different anions. So let me give one very simple example that we're going to come back to when we talk about examples of boundaries. Namely, the torical model is one example of a topological or a bosonic topological order describable by a tensor category. So it has 4 types of anyons, 1, E, M, and F. So we could understand this as a Z2 gauge theory. E is a Z2 gauge charge, M is a Z2 magnetic flux, and F is the bound state of E and M. The self-statistics is that 1, E, and M are all bosonic, and F is fermionic. And the fusion rules are very simple. Basically, E and E fusing with E or M fusing with M gives you the identity, whereas E and M are E fused with M to give you the fermionic excitation. And the S matrix, the mutual statistics, is summarized in this table. Namely, whenever you move E around M or E around F, there would be a -1 phase. So we'll come back to this model when we discuss examples. What exactly is anion condensation? And how are they related to boundaries and interfaces? So I think it is first proposed or suggested by Bias and Slingerland in 2008 that gapped interfaces or topological interfaces between different topological phases of matter can be understood by thinking that one phase has some of its anyons no longer conserved. As in, when we say they condense, we meant that they are no longer conserved across the boundary. Then such condensation would be is capable of characterizing a gapped boundary or gapped interface. So when we talk about anion condensation, we have to first of all specify the set of anyons that condense across this boundary. Across this interface. And W here is a positive integer that tells us how many, the multiplicity of the anion in phase A that participate in the condensate. Then as the condensate, so this phase B is where the condensate is condensed, becomes the vacuum of B. And so if the condensate moves across the interface, it becomes nothingness in B. And then for other anyons that are not condensed, if I try to move it across the interface, 2 things could happen. Either it moves across into B and remains unconfined, or it would be stuck at interface and it is a confined anion. It would cause energy if we were to move these confined objects into B. And each of these either confined or unconfined objects in B, they could be expressed as a direct sum of anyons in A. And they are also characterized by these W's, which are positive integers. In the specific, so here A and B are both modular tensor categories. They also, both of them have a braiding structure. And in the special case where B is trivial, which it has only one sector, the trivial sector, then this interface here would become a gapped boundary of A. And so it is realized, or it is suggested that first by Bias and Slingerland, that all the topological interfaces or gapped boundaries can be understood in terms of anion condensation across the boundary. And this decomposition of anions across the interface is an analog of decomposition of group representations. If I'm breaking a group into a different group, expressing representations of one group into a different group. So that is an analog. And as we're going to see, they are indeed some kind of representations. So as I mentioned, when B happens to be trivial, then the interface is in fact a gapped boundary, and there would be some special properties of the quantum dimensions when this interface is in fact a gapped boundary, and that is the total quantum dimension of the condensate, which is simply defined as the sum of all anyons that participates in the condensate multiplied by their multiplicity is in fact equals to the total quantum dimension of the phase A. When this is satisfied, when the condensate satisfies this condition, then this interface is in fact a gapped boundary of A, and we call this particular condensate a Lagrangian algebra. Okay, so we talk about the concept of algebra. So let's actually go into what this definition means. So when Bias and Slingerland first talked about anion condensation, they made a lot of guesses of what these condensate should behave like. They had lots of guesses, but it was only slightly later where the question was formulated in terms of some algebra in modular tensor category, that the condensate forms an algebra in the modular tensor category. So Bias had some work trying to formulate this, and it was Kong Liang who gave a very comprehensive definition of identifying the condensate with algebra objects in the modular tensor category. And in fact, it was pointed out by Kong Liang that the full characterization of this algebra, this is not some arbitrary algebra. In fact, it is some commutative, separable, special symmetric Frobenius algebra. So let me say a few words about each of these qualifier in this very long name. So first of all, what do we mean by an algebra in the modular tensor category? So as I mentioned, it is going to be the condensate, and so it would be a collection of anyons with some multiplicity coefficients. And to talk about an algebra, we have to talk about product in an algebra. And so the algebra, so to talk about the product in an algebra, we can express the algebra in terms of its basis. So this I, J, and K belongs to A. And we have to specify all these coefficients mu, and that corresponds to specifying the product of this the product of this algebra. As a Frobenius algebra, this algebra is also a bi-algebra. So not only do we have to decide how objects in A are fused together in a linear combination, we also have to decide how an object in A is splitted into two objects in A. So that defines the coproduct structure. And so as an algebra, it has a unit which tells you that something behaves like A is equivalent to 1 times A. So this is so something has to behave like a unit. And as a co-algebra, there's also a co-unit. A is equivalent to A splitting to A times 1. And being a Frobenius algebra means that the product and the co-product have to satisfy some properties, which is summarized in this picture. And this qualifier of being a special separable means that the product and the co-product are inverse of each other, and that the unit and co-unit has to satisfy this property. Being symmetric basically means the following. And being commutative means that the braiding between objects in the algebra are trivial. So in particular, this commutative is telling us that the anyons commute with each other. They have trivial mutual statistics with each other, and they also have trivial self-statistics. And so it means that all the anyons that are condensing are bosonic. They behave like bosons. And these qualifiers are basically, you could think of them as some physical conditions that you would expect if if A is going to become like the trivial object in the condensed phase. These are some properties that you expect should be true of the vacuum sector. So this is so much about how the algebra is defined, that defines the condensate, that characterize the condensate. Having worked out the condensate, we have to decide what are the boundary excitations or the interface excitations. And so, not surprisingly, they are the representations or the modules of the condensed algebra or the condensate algebra. The reason, the intuitive reason is that if I have some excitations in A, and then I move it across to B, across the into the condensate, then certainly multiple different excitations in A would become indistinguishable if they are related by fusion with the condensate. And therefore, they would the excitations in A would have to arrange to among themselves into multiplets under fusion with the condensate, and therefore they are actually modules or representations of the condensate algebra. So how to work these out? The way we work this out is that to specify a representation, we have to specify the left-right action on the representation. So M is the representation, and as a representation, as we have already mentioned, it is a collection of anyons. And the left action or right action is specified in terms of the basis. In terms of this basis, and there would be some non-trivial coefficients. So how do we decide determine these coefficients? Basically, we would require that we would have to require that this picture is satisfied. What this picture is basically saying is exactly what we would usually require representations to satisfy, and that is if I have the action of two A's, sequential application of A, it should be equivalent to first multiplying A and then acting on the on M. So that is exactly what we would require of representations. And so practically, what we usually do is that after having decided upon the product rule of A, then we can solve for these coefficients to determine all the representations of the algebra A in the modular tensor category. And then once we have determined all the representations, that tells you all the excitations that are allowed at the interface or at the gapped boundary. In practice, the way we work out these excitations is to use this so-called induced modules. It's really, it would be way too tedious if I actually have to go through working out all these coefficients. So there are some shortcuts. It is demonstrated in the mathematics literature that the representation category or the representations of a given Frobenius algebra is semi-simple. And so once I have, so I could first work out all the induced modules, and these induced modules would always be decomposed in terms of simple modules. And so by knowing what all the induced modules are, we usually can work out all the modules of the tensor category. So what are induced modules? Induced modules just means that I can look into fusing the algebra with any anion in the modular tensor category, and the left action of the algebra on this induced module can simply be defined using the product rule of the product of the algebra. So I'm just shielding this C in the tensor category by the algebra itself, and all the left action is basically the product of the algebra itself. And so this is one very quick way to allow you to work out all the simple modules, and we can make use of some conservation of quantum dimensions to help us in identifying the actual modules. So there are two very useful identities. So first of all, every anion, so if I want to know what kind of representations it would participate into that is characterized by this W, we'll find that the quantum dimension, so X is the quantum dimension of the excitations in the condensed phase, the quantum dimension of the condensed phase that A would participate into, they conserve. So the sum over all the representations that dA participate into is equals to dA itself. But on the other hand, we know that the quantum dimension of dx is equal again to the sum of all the participating A inside X divided by the total quantum dimension of A. So these identities can be proved has been proved in the mathematics literature. And I'll come back to these relations because they would be modified when we start, to some extent modified when we start talking about fermionic condensation. Okay, so we can work out in simple modules using induced modules, and we can also define fusion between different modules. So the idea is that if I have a product of if I have a product of two representations, how could I define the very much like in group theory, if I have the product of two representations, it can again be decomposed into simple representations. And so practically how that is done in the mathematics, we basically put in this line, which is A, that connects M1 and M2, so that now the left action on the composite object M1, M2 has a unique left action. Because if I act A on M1, it is based using the property of the algebra and of representation. I can basically shift this left action into a left action of M2. So practically, M1, M2 becomes a composite representation with a unique left action of A. And so, and supposedly this can be decomposed into some simple representation. Practically how that is done, it is one can use this orthogonality conditions that is just by Fuchs and friends, and also Kirillov and friends. These people, they worked out the mathematics of Frobenius algebra in a modular tensor category for a long time. So now these relations can be applied when we work with the edge excitations of a condensate. And so there are some orthogonality conditions. And so in practice, how we obtain how we decompose these product representations in terms of simple representations, we can use these orthogonality conditions. There's also a very useful identity that says that basically relates the fusion of any two objects in the parent modular tensor category with the fusion of the child tensor category. So this is also a relation that was proved in this older works, and this is something that we would use pretty heavily later. Okay, so I discussed slightly how to work out modules, how to work out their fusion for a given gapped boundary for a given condensate. So what about junctions and junction excitations? When we talk about junctions and junction excitations, what we meant is that there are two gapped boundaries and they touch each other at a point. So in general, which is shown here, and in general, there would be some non-trivial excitations that are allowed at the intersection, at the point where A1, where the gap boundary 1 and gap boundary 2 touch each other. So the excitations are localized at the junction in a very similar manner as excitations at each boundary. They are characterized by bimodules of algebra 1 and algebra 2, which I called A and B here. And as a module of algebra A and B, we require, as a bimodule of algebra A and B, we require that the left action and the right action commute. And so this is so it has to satisfy all the properties of modules for the left action and right action separately. And in addition, we require that the action of A and B should commute. So this is practically how we solve for all the bimodules, and in that way we would obtain all the independent excitations localized at the junction. Okay, let me say that these people have worked out how to obtain the fusion of these junction excitations. In particular, if I have a junction localized between gapped boundary 1 and 2, and then an excitation localized between junction boundary 2 and 3, then these two things can fuse into an excitation in the junction of 1 and 3. And in general, this is not a trivial problem. So I laid out a procedure, a recipe, but in general, working it out is not completely trivial. It's slightly easier. It's easier in the abelian case, and in the non-abelian case, it requires some more work. But then there are some formula that would help us into doing that, and that is something that I worked out with Shen Ce last year. And so there's there's a formula that is very much analogous to the Verlinde formula that allows us to work out the fusion rules of the excitations between different junctions. So roughly speaking, it would depend on some half-linking number between the condensed lines and the junction excitations. So I'm not talking about the derivation here. In fact, we're going to see a bit more of that. But it's basically based on the fact that if I move a condensed anion from A1 to A3, I could break it up into moving it first around first between A1 and A2, and then moving across from A2 to A3, and this equivalence leads to this formula. Okay, so that is a slightly extended introduction to the mathematics of anion condensation when the condensed anions are all bosonic. So now let's move on to the actual meat of this talk, where we want to talk about fermionic condensation. So fermionic condensation has been considered before. So even before the idea of anion condensation, so even they didn't use the words fermion condensation, but actually in this paper, they talked about a lattice model where anions, the fermionic excitation in the toric model could escape in the boundary. This paper had some discussion of some experimental setup. But to use the word fermion condensation very explicitly, it basically, I think, started in 2016 in these papers. It basically, the motivation, I think, in Gato and company, and also Lan Kong and Wen's paper, they were thinking about embedding a spin TQFT, a fermionic topological order, embed the spin TQFT into a bosonic topological order, and so basically use the classification of bosonic topological order to understand different spin TQFT, and the relationship between the bosonic order and the fermionic order is related by a fermionic condensation. And these papers also discussed some practical issues of how to recover the condensed theory from the parent theory. But these papers are mostly concerned about the case where the fermion that has been that condenses are simple currents. So in this current paper, in this current talk, we will be considering more general fermion condensation, and also we will also systematically work out the boundary excitations and also the junction excitations. When the fermion condensate is non-trivial, it could involve a non-abelian anion. So not surprisingly, to make this generalization from bosonic condensation to fermionic condensation, the ingredient that we're going to need is to generalize the notion of Frobenius algebra into a super Frobenius algebra. So let me say a few things about the ingredients that are going to be involved. So we have to understand what to expect in the condensed theory, and then we would be able to tell what are the things that we should pay special attention to. So the condensed theory itself is no longer simply a fusion category, but a superfusion category. So there are many definitions of superfusion category studied in the math literature, and I'm going to follow some minimal, and not all of these structures are necessarily relevant. So I'm going to stick to some definitions that could be found in this paper and this paper. I believe this paper of Gu, Wang, and Wen was the first to write down a super pentagon relation. And this is going to be the direction that or the framework that I'm most following. So what are the basic ingredients that go into a super fusion category? So first of all, as far as the objects are concerned, there would be two kinds of objects, roughly speaking. So first, there would be simple objects where the endomorphism, the maps, the morphisms between itself in itself is trivial. It's still one-dimensional. So that is what we already have in a bosonic fusion category. But we might also allow for objects that has non-trivial endomorphism, where the maps to itself is two-dimensional. It has one bosonic and one fermionic generator in maps to themselves. So this is the first non-trivial ingredient of a super fusion category. There are two kinds of objects: some bosonic type objects which has trivial endomorphism, and some what they called Q-type objects which has non-trivial endomorphism. In the case, and the second ingredient that characterizes the supercategory are the fusion morphisms, the fusions between objects. Very much like endomorphisms, these fusion morphisms now could also have both bosonic channels and fermionic channels. And in particular, this delta ABC are the fusion coefficients, but the fusion tree, the fusion basis would include the endomorphism of C. So this is a definition adopted in this paper. The bottom line that the bottom line is that so this definition here just ensures that when C is a non-trivial, when C is a Q-type object, the fermionic dot can be moved between C and it can be exchanged. You can move this dot that corresponds to the fusion channel being a fermionic channel. This fermionic, or you could think of it as a Majorana mode trapped at the fusion channel, can be moved to the can be moved between the anions. So that was the motivation of introducing this definition of the fusion channels. But the bottom line is, when we're dealing with a superfusion category, the fusion channels could be either bosonic or fermionic. And so when we look into the pentagon relations, we have to be very careful with whether the fusion channels are bosonic or fermionic. And if you look into the full different paths or different orders of fusing the anions, then you realize that the consistency condition would involve exchanging the labels of two of the fusion channels. And so if depending on whether these fusion channels are fermionic and bosonic, you may or may not get a -1 sign in this exchange. And so this is a new ingredient in defining the superfusion category. Moreover, so a third thing that we have to worry about is whether the objects in the fusion category corresponds to non-trivial, generate non-trivial spin structure. So if I put this particular anion wrapping around a non-trivial cycle, it would generate a non-trivial branch cut in the other cycle, and whether that branch cut is local or non-local to a free fermion, it would generate different spin structure. So it could either be a fermion, if it moves around this branch cut, do not gain a sign. That's some kind of Navier-Stokes spin structure. And if a fermion move across this branch cut and get a -1 sign, that would correspond to the Ramond structure. So in general, when we look into a superfusion category, what we have to worry about is whether the simple object is bosonic or Q-type, whether the fusion channels are bosonic or fermionic, and whether these objects in the category generate Navier-Stokes or Ramond spin structure. It might generate more non-trivial things if we are considering a general non-abelian fermionic condensation, but roughly speaking, it could be separated into either the Navier-Stokes objects that generate a Navier-Stokes branch cut or a Ramond branch cut with respect to the free fermions. Okay, so these are the things that we expect to show up when we condense a fermionic anion at the interface or at the boundary.
Anna, can you hear me?
Okay.
Yes. Oh, actually,
yes.
I've heard you several times already. But anyway, would you give some examples for those?
Yes, I will. So I'll give some example. How much time do I have? Or do I have to speed up a little?
No worry, at least 40 minutes. You still.
Okay. So it would not. I will not rush it, but I hope that it is clear. If there's any thing that is unclear, please let me know. So I just described what we want to we should look for in the condensed phase. So now let's go into the meat. How to define super commutative symmetric separable Frobenius algebra. So the extra thing that goes into defining a fermionic condensate really is just this super commutative part. So compared to the bosonic case, the structure of the algebra now is super. And so in a super algebra, so again, there are lots of definitions of super algebra, and we are going to, we followed some of the things that are described in this paper in 2017. And the basic structure that we're adopting is that in this super algebra, it can be decomposed into the direct sum of two components, the bosonic or the fermion parity even part and the fermion parity odd part. And so we have to define fermion parity of the anions that participate in A. And once you have such a decomposition, then we can define the meaning of supercommutativity. Supercommutativity just means that when we look into the braiding of two anions, if both of them are fermionic, then their braiding is defined as having a fermion, having their braiding R matrix in the tensor category where these objects live, and multiplied by an extra -1 sign. So that is how supercommutativity is defined. For example, in this paper, physically, what it means is that if you want to allow these fermions to condense in a consistent way, then you have to bind fermion to the fermion participants in A, so that ultimately they behave like a boson. So I think this is basically what this supercommutativity means, that if a if the anion is not bosonic, supposedly it's not consistent to condense it, but the inconsistency is mild enough that I could fix it simply by binding it to another fermion. And I think this is one way to understand why after the condensation occurs, you obtain a spin TKFT, because you basically have to couple it to the spin structure or couple it to free fermions in order that this fermionic object can condense consistently. So let me comment that it remains true that if the algebra, if this superalgebra describes a gapped boundary and the quantum dimension, yes.
Let me add something, maybe
sure.
questions. These are pretty general, but let me ask something more basic. Earlier you said that for fermionic condensation, it seems like the spin structure data, like periodic, anti-periodic boundary conditions, anti-periodic NS and the periodic Ramon, those data will come in, is that right? You need those data?
That's right.
And is that data only associated to like a 1+1D boundary, or does it require also some data from 2+1D theory?
Okay, this is a great question. So when you condense, so it's not necessary that it is a topological gapped boundary. It is also possible to obtain interface between a bosonic and a fermionic TQFT. And so actually, I think you can have, so I think there is data about a two-dimensional spin structure. So I think it's more than just I think it's more than just it's more than just 1D data there. But in practice, in what we are discussing in most of our work, we are only talking about the 1D edge. And so in that case, I think I can treat it as a 1D problem. But so this is a very good question. So in fact, when we let me see, did I? Okay, it will come later. I'll comment that when we work with, so we will be able to obtain the 6J symbols of the condensed theory, and so that you do have to specify a bit more data to recover the 6J symbols, and the data of the spin structure has to be included in some delicate way. So there is a lot more data than I've just. I think there's more data than the 1D problem.
A more basic question. I think what you described so far is very, very probably abstract or general. But for audience, maybe more condensed matter, we can help them a bit. So I also question on that. Say that if we just take a Z2 gauge theory or Z2 torical, we know that in such a 2+1D bulk torical has two types of gap boundary on 1+1D edge. Either
That's right.
Condensed or M condensed. And while the Z2 double semions twist the Z2 gauge theory, or known as diagonal Witten with cohomology twist, that's one type of boundaries, which the semion and the semion bar condense. So since you also Fermionic case, do you have a gap boundary, for example, for Fermionic type of a Z2 gauge theory? For example, in 2+1D data ZA class, are there such a data you can obtain later? You might show people about this.
So I'm going to the specific example that I'm going to talk about. I'll talk about two examples. One example is this torical example in which there is a fermion. If you remember when I flash the data of that topological order, and that fermion indeed can condense. And I want to that is one example that I'm going to show.
Okay.
And another example is a non-abelian example involving the S3 gauge group. S3 gauge theory, or S3 quantum double, as it is known. So I talked about, I mentioned spin structures, but the actual information that is going to need, that we're going to need is less than that. I'm not going to make use of all the data about spin structure. I'm just going to show which of the anion correspond to Navier-Stokes or Raymond anion, and which of the fusion channels are even or odd. That is going to be the focus of the talk and of the paper, in fact. Does that make things clearer?
Okay, you'll give two examples at least later.
Yes, I will give 2 examples.
Okay.
Let me see. Okay, I will not spend so much time into. Sorry.
Sorry, I have a question. Just to try to understand your general setup here. So in this slide, this is C. C is a modular tensor category which describe some topological order, right?
Yes.
Yeah, and then this A describe. My guessing can I understand this A, this super algebra, describe a boundary between generic topological order and a particular topological topological order, where the fermion can kind of go through the boundary. That can be an understanding of this.
It is between a generic topological order and nothing, or a trivial spin QFT. Yes.
No, in this case, you say it's between the generic topological order and another trivial phase, but this trivial phase is the fermion product state.
Yes, I agree. Yes.
But however, this fermion product state can be viewed as a Z2 topological order, where this which have a fermion which provides the trivial fermion. So
yes.
So I wonder if this A is some kind of particular boundary between Z2 topological order and the generic topological order. That's where the fermion can go through the boundary.
That's right. Yes.
Yeah, that's one way to understand. Thank you.
It is.
Yeah.
Yes, that's correct. Right. So I was about to comment that the quantum dimension, if the boundary is between a generic bosonic topological order and the trivial fermionic order, which has, as Hexagon was pointing out, just the trivial sector and a free fermion, then the quantum dimension of this algebra is also equal to the quantum dimension of the this bosonic order with which we're describing the boundary. And so I believe this is called some super Lagrangian algebra. Okay, so now practically, how do I work out the excitations of these on the boundary? So remember, we were worrying about, first of all, understanding whether these are Q-type objects or bosonic objects with non-trivial endomorphism. So what we realized is that if the excitation, so these excitations are again modules or representations of this super Frobenius algebra, and when the representation, when the module has non-trivial endomorphism, what it means is that you would be able to solve for 2 independent left actions of the algebra on this module. On the same group of anions, you would be able to find 2 independent set of left actions. So actually, this is something that we sort of know, even in bosonic algebra. If a bulk anion splits into multiple modules, you can also find independent left actions. So we have to distinguish the situation where a bulk anion participates in several different modules, or it has non-trivial endomorphism. To distinguish these 2 cases, there would be several identities that are known in the math literature that help us. So I'll not waste too much time on the detail. So we basically use a lot of these identities in the mathematics literature, and we find that, for example, the identities that are known in this mathematics literature have to be slightly modified in order that to accommodate for this non-trivial endomorphism. So for example, the quantum dimension of an object of a representation is equals to the anyons, sum of the quantum dimension of anyons participating in these representations multiplied by the endomorphism of M divided by the quantum dimension of A. So in the past, there's no so this is the dimension of endomorphism of M. It was just one in bosonic condensate, and when you work with fermionic condensate, then you realize that you have to put this factor in there. And basically, the idea is just that if M is a Q-type object, is a fermionic excitation, then this kind of action, left actions, would have in two copies, and therefore, when you try to compute this diagram, you have to sum over the contribution of the two independent left action, and then you end up with a new factor here. But even with this new factor, it is still true that we find that it is still true that quantum dimensions of the parent of anyons in the parent theory and is still equals to the sum of the quantum dimension of the daughter theory. So there's still conservation of quantum dimension. Let me see. I want to go into the examples. So I would just say that so when there are two sets of two sets of left actions, then you realize that some of the formula that were known in the math literature gets modified. So you get factors of the endomorphism of the representation all over the place, just because the proof of this formula is based on summing over these left and right, summing over these left actions, and because a Q-type objects comes with two independent left actions, you get this extra factor. But the important point is that quantum dimension remain conserved. So because and this formula relating fusion rules of the parent theory and the child theory remains true mostly. And so we find a modified version of the defect of Verlinde formula, which not surprisingly is again just modified by factors of the endomorphism. And now we also have worked out a way to compute the half-linking number from these topological diagrams based on the left and right actions of the algebra. So these are just some details. One quite interesting observation that we made before is that this half-linking number can be worked out very simply in terms of the S matrix and W matrix. This S matrix is the S matrix of the parent modular tensor category. And this I, when you take the sum of K with WKX, so I fix a very specific boundary excitation, and then I sum over all the K with W. This sum automatically ensures that this I index is only this combination is only non-zero when I falls into the condensate, and also this V is a square matrix. I don't know if there's a physical proof that I could give why what it means is that the number of anyons that shows up in the condensate is always equal to the total number of excitations in a gapped boundary. And physically, you could understand that just because if you consider a cylinder, I can construct two sets of bases, ground state bases. Either I have confined anyons wrapping the non-contractible cycle of the cylinder, or I have condensed anions that connect between the top and bottom boundary of this cylinder. And if the total number of ground states, the ground state degeneracy is a physical quantity, then it better be true that the two ways of constructing a ground state basis be identical. And so somehow mathematically it means that this combination is always this V defined here is always a square matrix. Okay, so the reason why I dwell on it is that we mentioned previously. Yes.
What do you mean by square matrix? Some matrix square? What do you mean? Just make sure.
What I mean is that so I takes values in C in the number condensate. X, the number of different X corresponds to the number of different excitations. The number of different excitations, the number of different X label is the same as the number of I label, the number of species in the condensate. So is that
I don't understand. What does C has to do with square? You mean the number of condensations, like half of a, or maybe square root of quantum dimension of a total dimension or something like that? For example.
No, I don't. I mean that, let's say if I am in a toric code and one of the boundary is characterized by the magnetic condensate, then the number of different condensed particle is 2. I have either the trivial sector or the magnetic charge sector. So there are 2 different condensed anions. And X is the number of confined excitation. So I would include the trivial excitation also as a label X, because that is the trivial representation of the algebra. So X also has 2 labels in that case. It would correspond to the trivial sector or E plus F, which form a multiplet of the condensed algebra. So the number of condensed things is always equals to the number of confined things, and that has nothing to do with the quantum dimensions.
Why is, I don't understand. Sorry? Why is it related to square? What do you say square here?
The number of rows is the same as number of columns in this matrix.
Okay, that's what you mean by square. No problem. Thank you.
Right. Sorry. So the reason why I dwell on this is that we have been laboring about the fact that fusion channels could be either even or odd. And so now, how do we distinguish even and odd fusion channels? We find that there's a very neat way of recovering it. And basically is that you define a twisted version of the algebra. So basically, if the anion involved is a fermion, then let's twist it by a -1 sign in the definition of this A tilde. And then when you when you fuse this A tilde with the anions, it would generate for you this some linear combination characterized by this so-called omega matrix. And the omega matrix, so the omega matrix is basically just telling you the anions involved in a representation, but it has a minus sign whenever the parity of the anion involved also have opposite parity, opposite fermion parity compared to the other members in a representation X. And in particular, if I want to look at the fusion of anions in the condensed phase, I can obtain it from the parent theory, but then fusing the anions in the parent theory in addition to this A tilde, then I would just this linear combination in which this N tilde XYZ is basically the number of even fusion channels subtracted by odd fusion channels. And so in that way, you would be, in the previous slide, here, this NXYZ is really the total number of fusion channels between the boundary excitations X, Y, and Z. It is adding up both even channels and odd channels. And in this slide here, this N tilde XYZ is basically giving you the difference between the even channels and the odd channels. And so with that, you can derive a twisted version of the defect Verlinde formula, which turns out to take this particular form. So you can derive this formula basically starting from this equation here. And so the thing that I'm laboring upon is that this little v came from contracting the S matrix of the parent theory with this omega matrix that I have generated by looking into this fusion relation. And it turns out that so the final so this M endomorphism here is also the even channels subtracted by the odd channels. So in particular, it would mean that if X belongs to a Q-type object, this is identically equal to 0. And so finally, the sum would involve only XYZ that are not Q-type. And it just turns out that when you look into this final formula, it involves this little matrix, little V matrix. And so it is saying, it just happens that the number of anyons, the number of excitations that are not Q-type is equals to the number of anyons in a very specific representation called XF. And XF is basically the unique Ramond-type anion in the condensed phase. So the Ramond-type anion, I mean that when you it generates a -1 whenever a free fermion pass through run around this Ramond-type excitation. So there's a when you have a gapped boundary characterized by a fermion condensation, there is a unique anion that is responsible for generating this -1 fermion parity. So you could think of it as a Z2 fermion parity defect, and it is that you could think of it as a fermion parity defect, and the number of anions participating in this fermion parity defect is always the same as the number of non-Q-type objects. This little v is a square matrix. I don't exactly know why this is an observation in deriving this formula. Okay. So this is just some.
Excuse me.
Sorry. Yes.
In the earlier defect Verlinde formula, you try to relate the fusion rule, the fusion algebra on the 1 + 1D, say, boundary to some half braiding gamma, right?
That's right.
And that gamma is related to this V matrix that can be obtained by the tunneling matrix of W and also the modular S matrix.
That's right.
And V matrix, you say, is a square matrix. So it's the half braiding gamma matrix is also a square matrix?
Yes, it is. They are directly proportional to each other. It's a square matrix.
And this is an obvious physical fact that it seems like maybe several slides ago, you should already have this fact, but it seems like after several slides, you emphasize this fact. So I wonder, why is this fact only emphasized in this slide, not maybe 10 slides ago?
Okay, because previously I didn't emphasize it, but I emphasize it here because the derivation of this formula requires taking inverse of V. If it is not a square matrix, I wouldn't have been able to take inverse. And so it becomes more, it becomes a more prominent fact to us when we were deriving this formula. So this issue sticks out when we looked into this formula.
Earlier, when you write the earlier version of defect Verlinde formula, that half braiding gamma also has an inverse in the formula you write, right? So
yes.
So I mean, the fact is the same. I mean, the reason is still the same over there. It's the same as the one over here.
Yes. Okay, but so the point that I'm important point here is that we're able to distinguish the even channel and the odd channel in the presence of a fermionic condensate. And so I mentioned briefly, sorry, yes?
And the Q types, you mean the electric type? I forget the notation earlier, the Q type. What do you mean by Q type? Maybe M type in the table.
Right.
What does it mean?
Sorry.
What does it mean? The Q type, M type? I don't remember.
Okay, so the Q-type objects are those which has non-trivial endomorphism. That the maps, so it means that these Q-type objects can trap a Majorana fermion. You could think of it as. So it means that objects with non-trivial endomorphism have non-trivial maps to itself, which is a two-dimensional space of maps to itself. One with even fermion parity and one with odd fermion parity are called Q-type objects. Is that?
How about M type? It looks you also have an M.
So M-type objects are basically the what I meant bosonic objects with a trivial endomorphism space, which is one dimensional, only a trivial map to itself, that identity.
Okay, thank you.
Oh, sorry. So I think I'm running late. So let me just say that. We actually worked out an example how to recover all these XJ symbols of the child theory, and there would be a more detail required on how to deal with the spin structure. We learned a lot of that from Dave's paper, and he actually explained a lot while we were working things out. But I'll not go through this detail here. So let me just say that then you have to go through very similar things in junction excitations. And there were very useful identities derived for junctions, which are bimodules. And some identity that tells us how to compute endomorphism of induced bimodules. And we use this identities to tell whether an object is a Q-type object. And we also derived a defect Verlinde formula for junctions that has to take into account endomorphism. In this case, we didn't really know how to derive the twisted type of the defect Verlinde formula. We only obtained the sum of the sum of all fusion channels. But so this is something that could be done in the future. So what I really want to do now is to move on to examples, because I think I'm running really late. And
no rush.
Sorry?
No rush. Take your time to stay. No rush, please.
Okay. So sorry, because I think I've delayed some detail for way too long. But there is something very interesting when we talk about junctions between when we talk about junctions, excitations. So so far, when we work out gapped excitations on the gapped boundaries, it seems that we're still following the playbook of working with representations of Frobenius algebra in a bosonic modular tensor category. But when we try to work on these junctions, then we ran into a problem, which we will demonstrate in the examples. But roughly speaking, the problem is something that has been talked about before in this paper on abelian gapped boundaries. And these Xiaoliang and friends, they talked about also cases of gapped boundaries involving fermionic theories, and they already noticed that junctions can trap Majorana mode, extra Majorana mode. And so whenever you put an extra Majorana mode into the junction, then you change the quantum dimension by a factor of √2. So the thing that bothers us for a while was that we realized when we work with these fermionic junctions, or this condensation, when we work with these junctions, the categorical description gives you some fusion rules. But does it include or not include this extra Majorana mode? It just shows us that when we work through examples, we realize that sometimes it's not avoidable that extra Majorana modes have to be included when you fuse between different junctions, namely that the categorical way of describing these junctions would give you a canonical description of the junction. But then as you fuse them together, it would generate for you copies with extra Majorana mode. And we have to find a way to we have to find a bookkeeping device to remember what are these extra Majorana modes and how they are showing up when we fuse different junctions. So this is really the extra little bit of ingredient that comes in when we deal with junctions. So without further delay, let's go finally into examples and see how things work. So the first example that we are going to talk about is the toric code model. The topological data I have shown you before, it has 4 sectors, 1, E, and M are bosonic, and F is fermionic. So there is a fermionic boundary that characterizes the toric code model, namely the fermion can condense. And so there are 2 excitations in the boundary, the trivial excitation, which is just 1 and F, and then and also what we call XF, where E and M are identified and they're stuck at the boundary. So actually this situation has been considered before in Galto and company's paper. They discussed the possibility that F can condense in the toric code. So XF is a confined object, and it is easy to work out the fusion rules of XF using the tools that we have provided in the previous in the previous slides that we have discussed. And it's not hard to show that XF fused with XF to give the identity. Now let's do something slightly more interesting. As Juven has mentioned to us, there are 2 known bosonic boundaries that are already known for toric code. So one bosonic boundary is characterized by condensing E. There's another bosonic boundary characterized by condensing M. And if I condense E, there is also one non-trivial confined excitation trapped stuck at the electric boundary, which is where M and F are identified. And similarly, there's a non-trivial excitation trapped at the magnetic boundary where E and F are identified.
Excuse
me. Now,
yes. I need some help. If I need some help, yes. I think the audience also needs some help. Please,
yes,
one slide earlier, please. Yes.
Yes.
So in the usual way, I understand this W matrix, which you refer to as a tunneling matrix. This will be the labeling of the tunneling data from the bulk anions on the top.
Yes.
Whether they can move to the boundary. And the first row saying that the trivial and also the fermionic F can move to the boundary, correct? There's someone
yes.
in the Zoom bumpy to write this. Please remove this, please. I think the audience should have self-discipline. Please remove. Otherwise, if we identify someone write this.
Oh, okay.
Please remove. Thank you. So how about the second rule, the confined object, XF? I don't understand that part.
Okay, XF, I just mean that E and M, they are the representation of the algebra 1 plus F. So this is slightly more than the tunneling matrix because it includes information about things that are confined. And so here one says E and M are both participating in XF. The confined object at the boundary, they are identified. Is that clear what it is?
Oh, so what's the rule or what's the meaning for the second row in the matrix?
Okay. So
There's
the second row. So remember, right, that's right. In the past slides, I was talking about how we work out the excitations at the boundary. So the excitations at the boundary are representations of the algebra. So what we need to do is to look for all the representations of the algebra inside the tensor category. So every representation would correspond to a direct sum of several different anyons in the bulk theory. And this W matrix here is telling you that E and M together form a multiplet of as a representation of this algebra 1 plus F. And each of them participates into this representation XF once. So that is what it means. So if you try to work out all the possible representations there are for this algebra 1 plus F, then you find that there are only two representations. Either 1 plus F itself is its own representation, or E plus M as a multiplet forms a representation of 1 plus F. Is that okay?
And how about the big omega? I'm not sure I remember the big omega definition.
Right. This omega is telling you the fermion parity of the objects inside the given representation. So for example, trivial representation is 1 plus F, and then 1 has even fermion parity, so it has 1. And then it has odd fermion parity. F has odd fermion parity, and so omega is -1. Here, and then using the rule of fusing 1 minus F with E and M separately, then you would realize that I can assign even parity to E and odd fermion parity to M. And so this explains this -1 sign here. So sorry, I didn't explain it because
No problem.
it doesn't, so we're not going to use it in the example for now. So
certainly,
I skipped it.
EM can exchange here. EM can exchange here.
Sorry. Yes, there's a sign ambiguity here. They only need to, so we can fix omega up to some overall sign. So mention we are fixing E to have positive parity and M to
Hello? Not sure whether the internet break off on my side or your side, but hello?
Parity.
Hello? Hello? Thank you, that's fine. Thank you. It helps. Damn. That's strange. Hello? I'm not sure. Hello, is Jenna still here? Hello? Can people hear me?
Yeah, I can hear you.
Yes, I can't hear you. I guess her mouse is moving, so she's here, but she can't hear you, Envy.
Okay, but right now we cannot hear Jenna now. Oh,
Muted.
Janet.
Hello, is it better now? Hello?
Yes, by the way, you muted yourself earlier, so there was no voice. You probably should repeat these slides, but thanks for the explanation, that helps. Thank you very much. This slide may
Okay, thank you.
this one again. Earlier you muted yourself.
So,
You had to mute yourself, so you need to explain this slide again. Sorry about this.
okay, I'm sorry. Okay, so let me just continue with junctions, right? Okay, so we have a bosonic, we have other bosonic gapped boundaries of the toric code. So the characterized by the electric condensate or the magnetic condensate, and on the electric condensate there is an excitation that corresponds to the magnetic charge and the fermionic charge forming a multiplet. And similarly, in the magnetic condensate, there's a non-trivial confined excitation corresponding to the electric and the fermionic charge forming a multiplet. So now let's consider junctions of the fermionic and the electric condensate. So we can work out bimodules of the electric algebra and the fermionic algebra. So it is going to tell you that exactly all the anyons would have to come together, form a single multiplet in the bimodule. And you can work out the fusion rules of the of this excitation with itself, and it is using the rules that we have discussed in the mathematics literature. You'll be able to find that it gives you the identity. So if EF fused with FE, it should give you excitations in the electric condensate. And so it tells you, if you work things out, it tells you that, okay, I would get the trivial sector and also the electric confined object. Similarly, if I work out the fusion of Fe and Ef, then it should give you the boundary excitations of the fermionic condensate, and it would give you, it would tell you that it is the identity object and also the fermionic and also the excitation in the fermionic sector. So these fusion rules are telling you that XEF should have quantum dimension square root 2. Because two of them together, the product of two of these things gives you total quantum dimension 2. This is 1, this is 1. So you can do the same thing to the EM boundaries and look at the excitations at the EM junctions. And then you will find that the EM junction also has a bimodule that is exactly given by a multiplet involving all the anyons in the toric code. And if you work out the fusion rules of this EM junction, you will find that it also has quantum dimension square root 2. So both XEF, XEM, and XMF all have quantum dimension square root 2. So this would lead to some confusion. And the confusion is that now consider fusing the junction of EF and the junction of FM. Then you would get a junction of EM. If I follow simply the representation, looking at representation of the bimodules EM of E and M, I have one unique representation, which is 1 EMF with quantum dimension square root 2. But in each of this junction, I also know that the quantum dimension is square root 2. So it doesn't make any sense because the fusion of this guy, has quantum dimension square root 2. This guy has quantum dimension also square root 2, but then the product of the fusion still has quantum dimension square root 2. And so it tells us that what we have learned simply using the bimodules of the fusion category has something missing, because this number here should be an integer. But we would not be able to make quantum dimension conserve if we just follow what we have learned from the representation of the algebra of the modular tensor category. So what we realized is that, so we looked into the lattice realizations, and we realized that so we look at the we look at the lattice realization of this situation of E boundary, F boundary, and M boundary. And so we realized in these lattice models that actually the number of Majorana modes that are trapped in these two junctions cannot be the same. Or in other words, the total number of Majorana modes trapped between these two junctions have to be an odd number. There must be some odd number of Majorana modes shared between these boundaries. So how do we understand it from the point of view of the category theory? And so we came up with a trick. It probably should have some proper mathematical formulation, but right now we use it as a trick. And that is, let us remember that F itself cannot condense itself. It really is a bound state of the fermion with this fermionic anion that it condenses. Let's keep the free fermion when we represent 1 plus F in the condensate. Then when we look into the fusion and keeping this free fermion and then follow the rule of fusion modeled out by 1 plus F is F, if AF is in the middle, then we would come to a final equation, a final result that looks like 1 plus E plus N plus F times 1 plus psi 0. And we interpret this 1 plus psi 0 as basically a Majorana mode that is trapped at the an extra Majorana mode that is trapped at this junction. So basically, we introduce a bookkeeping device when we work with these junctions, and we find that these bookkeeping device that tag every fermion with a free fermion would be able to recover for us the correct quantum dimension. We would be able to help us to count the number of Majorana modes that are actually trapped at these junctions. So I hope I have been able to explain this point, and that is, if you just follow the bimodules rules of solving for modules in the tensor category, then you would miss out some Majorana modes in actual fusion. And when we stare at the lattice models, we realize that the modular tensor category is not accommodating, it's not describing all of the Majorana modes that are actually appearing. The fact that these two junctions are not identical. One of them has an extra Majorana mode compared to the other. And so the way we deal with that is that we introduce an extra free fermion into to tag the fermionic condensate. And we find that if we do that, we're able to recover the we're able to count the number of Majorana modes that are finally trapped. So, so the bottom line is we need some extra tool to remember the number of Majorana modes that are trapped at each junction when we deal with fusion of these of these junctions.
Right,
yes?
I have a question. So in the left figure, where's the Majorana mode? You say there's one extra Majorana mode there, but which junction is it?
Okay, so precisely which junction? You mean this junction or that junction? Is that the question?
Yes, yeah.
So when we stare at a very specific lattice realization, so in this lattice realization, so this is basically the Wann plaquette model. And at every point where a fermionic operator, the fermionic line operator could end, there is one has to add a Majorana mode.
Yes. Janet, I think you are muted again.
Hello, hello. Sorry, unstable connections. I'm sorry.
No, it's okay.
Am I clear? Am I? Is it clear? My voice is back.
Yeah. I
Can
can
you?
hear you now. But I couldn't see the slide.
Okay, so I have to share screen again. Yeah, I was kicked out because my VPN was no good, and I
Oh,
realized that if I don't use VPN, I couldn't quite use Zoom. I'm sorry.
I see.
Sorry, I'm not allowed to share right at this moment. Juven, can you? Okay, now I'm allowed to.
No, I think you are co-host.
Okay, good. Sorry.
I think my
Now,
question was, in the toric code, there's a E and M exchange symmetry. So I thought E and
right,
M are on the same footing. But then I'm
that's
confused.
right.
Where should I place the extra Majorana mode at?
Yeah, I think this is a brilliant question. So, uh, so I'm trying to explain it in terms of the lattice model. And so basically, all we know is that at the gapped boundary, so there would be some, at the gapped boundary, there would be some Majorana modes, which you have to add some Hamiltonian to gap it out. But there would always be an odd number of Majorana modes left between M and E. Even if it is, so we know that when there's just M and E, there would be exactly one Majorana mode trap. Now, if this junction is extended into a fermionic boundary, there would be many Majorana modes. And so I have to add some Hamiltonian, boundary Hamiltonian, to remove the ground state degeneracy, to make it gap. But no matter how I choose the Hamiltonian, I would always have some odd Majorana mode that is left out that cannot be paired, and it would be left behind as some unpaired Majorana mode. And so whether the Majorana mode is either here or somehow some arbitrary location here, it depends on the precise Hamiltonian that I choose. So in some sense, it's not exactly right to say that I have an extra Majorana mode on the left or on the right. It's that I have some freedom depending on whether I choose some Hamiltonian that breaks some translation invariance or how I'm pairing boundary. It depends on the precise details of how I gap this out. But ultimately, these two things must have one, altogether it must have one unpaired Majorana mode. That is the lesson. Does that answer your question? So you're absolutely right that E and M are symmetric. So I can't really decide where that Majorana mode is. And the way I decided is by choosing the Hamiltonian that actually gap out the AF phase. And the tag that I'm putting in here is just only helps me to count the number of Majorana modes that are left finally. It doesn't really tell me precisely whether it is on the left junction or on the right junction, because for this exact space between E and M. Does that help to answer your question?
Yeah, that helps. Thank you.
Okay. So let me go to the final example. Sorry, it took such a long time. And the final example that I want to talk about is this S3 quantum double. And there's also a fermionic boundary that is characterized by ACE. So E is a fermion, but now it is non-abelian, as you can see. The quantum dimension is 3. And so this is one example of a non-abelian fermionic boundary. So one way to help us understand this example is that this example is not too different from the toric code model. And that is, in order to see that this example is closely related to the toric code model, you could understand it by condensing A and C first. If you condense A and C, then you realize that the excitations in this intermediate phase where A and C is condensed is precisely the toric code model the excitations came from multiplets of the parent modular category, but then there would be some confined sectors that are not found in the modular fusion category of the toric code, but then these objects would have been confined in the toric code model. But here they would be sitting there because now we're only requiring that the child phase, the excitations at the boundary, forms a fusion category. And so then this AF boundary would correspond to, after condensing A and C, I further condense the fermionic excitation in the intermediate toric code model. And so you can work out, so if I condense ACE, the fermionic excitation, I will find that at the boundary, I have exactly 3 different kinds of gapped excitations. The trivial excitation, the XF excitation, this is exactly the same excitation for the fermionic boundary that we have already discussed in the toric code model. The new thing is this guy that came from the confined stuff when in the intermediate phase. And so you can work out the fusion rules. That is standard. So now let's consider junctions in the DS3 quantum double. So let's consider in the intermediate phase, I could have chosen the magnetic charge to condense to generate the magnetic boundary. And as we have already learned in the previous toric code example, we know that there is also excitation at the magnetic boundary. Now there's one extra stuff corresponding to the confined stuff in the intermediate phase that also forms a non-trivial excitation at the magnetic boundary. So now we can work out excitations trapped at the junction between the magnetic boundary and the fermionic boundary. And you'll find that there are 2 independent bimodules. One corresponds to basically this object here in terms of the language of the toric code is 1 plus E plus M plus F. This is something that we have seen before in the previous example. This is new. This junction excitation corresponds to the confined stuff in the intermediate toric code phase, and it is given by D plus E plus F plus G plus H, a long bunch of stuff. So what is quite interesting is that this is a bimodule. It's also a module of M, and it is also a module it is also a module in the AF boundary. So the same linear combination just shows up both as modules of AM, AF, and also as a bimodule. And so now so this part, this guy, 1 plus E plus M plus F, this guy is easy to understand. This guy is a little bit tricky. And so this is an example where this is at the junction, and it is a Q-type object. The way we realize, the way we find out that it is a Q-type object is again that when we look into the fusion rules of this guy, we find that the quantum dimension doesn't conserve. It's not conserved. Very similar to the problem that we discussed before, and so we suspect this might be a Q-type object. And so we use this identity we use this identity that I discussed that first shows up in Fuchs' paper, and we find that this ZMF has an endomorphism which has a dimension equals to 2. So ultimately, this is the first example where we show that at a junction, this ZMF excitation really is a Q-type, is necessarily a Q-type object. And we confirmed it by solving explicitly for the left and right actions as a bimodule, and we find 2 independent solutions to the bimodule, demonstrating that indeed as a categorical bimodule, it is a Q-type object with non-trivial endomorphism. You can find 2 bases for this bimodule. So finally, in order to understand the fusion rules of this object, it turns out that we still want to tag it by these fermions. But in this case, because after the fusion, these M's, after the fusion, we started from two junctions, and then it just fused into an excitation of the M boundary. So MF and FM fuse into an excitation of the M boundary. And so now this size 0 tag is no longer trapped at a codimension 2 defect. It's now running free in the entire M boundary. And so all this size 0 is telling you is no longer telling you that there's some trapped Majorana mode, but rather that in fusing these two things, the fusion channel has both an fermionic parity even channel and an odd parity channel. So this is now giving you a factor of 2 rather than square root 2, accounting for a factor of 2. This is a curiosity of this bookkeeping device. If it is at a junction, it is accounting for a square root 2 quantum dimension factor, but when it is on an entire on a one-dimensional space, which it is running free, it is actually telling you that it is accounting for factors of 2. And so altogether, we find that the quantum dimension of this ZMF junction, this object, this bimodule object, actually has quantum dimension 2 square root 2. As a left module of M and F separately, it has quantum dimension 2, but as a junction, it necessarily has quantum dimension 2 square root 2. So this is some curiosity that came from it being a Q-type object, only when it is a bimodule. When it is a left module of AF, it is actually an M-type object. It has trivial endomorphism. But as a bimodule, it necessarily has a non-trivial endomorphism. We've also worked out the half-linking number and check the defect Verlinde formula, but let me not burden you with such further details. Let me just summarize and conclude. We have looked into fermionic gapped boundaries, and so hopefully it might have some applications these things hopefully have some applications in understanding topological defects of spin CFTs. Maybe it could constrain RG flows, and we would be very interested to understand how these things can be generalized in higher dimensions, and maybe understand in the future, maybe it would be very interesting to understand also gapless edges and how they are connected to categorical symmetries. But let me not say more things. Let me end here. Thank you very much.
Thank you very much, Janet Kong, for the very wonderful lecture. Any question from the audience, please feel free. Maybe you can move one slide earlier.
Oh, sure.
Feel free. Comment questions. Thank you.
Yeah, sorry for having taken so long. If you have technical questions computing certain of these things, then Chantal, ask you are free to contact them. They know every single detail of how to compute these things. They're experts.
Maybe Xiaogang is trying to ask something, but we cannot hear you. Maybe now you can. I think Xiaogang tried to add something.
Yes, somehow I couldn't hear anything.
May I ask a question first?
Of course.
Yeah.
Yes, please.
This is maybe more of a comment. So about the Majorana zero mode, I think maybe the thing you described is related to an anomaly in 1+1D. So in 1+1D, in 1+1D fermionic system with boundary, there's a well-known mod 2 anomaly discussed, for example, by Digraph and Witten.
I see.
It's basically about, it's basically saying that the system is anomalous if you have even or odd number of Majorana zero modes on the gap boundary. It's an anomaly in the 1+1D system, so it's not completely the same as your setup, but it could be related.
I see. Thank you. That's something I should look at. I'm not familiar with that.
I think Shuhan meant the most recent Dago-Witten, the second Dago-Witten.
Yes. The 2018 paper, not the one. Yeah, thanks for that clarification.
That was the second collaboration after 30 years, maybe 30 years.
I see.
I think Xiaogang tried to add something, but we cannot hear you. I don't think he has VPN issues, so I don't know.
That's true. He shouldn't have VPN issues as I do. My mic does not work, he says.
Maybe we can try to guess his mind.
Or maybe he could type a question or an or.
There's another way. Maybe Xiaogang can call me on Skype and I can use that Skype to broadcast the question. Xiaogang, if you can hear me, you can call me on Skype. That's probably a way. Okay, so maybe Xiaogang can ask now. So any other questions? I mean, certain people can interrupt or ask something more details if you want.
Oh, sure. Yeah, sorry for running vastly over time.
I was muting myself. I'm trying to say thank you first. Let's thank Jenny, Ling and Hong for a wonderful lecture, and people can ask later. Let's thank Jenny. Thank you.
Oh, thank you very much.